Assalamu alaikum. Today we have to look at the radiation heat transfer unit of Solteq model HE155 we have here in our lab. We will look at the different components and functioning of it. First of all, we will go to the bench. Here you can see the different components. Okay, this one has a radiation surface. Okay, this one is basically down the surface. There is a filament that is basically hitting the surface. So that's a hot surface. So we are not required to touch that. It's hot. And right in front of that, we have a radiometer to measure the intensity of the radiations emitting by the surfaces. Okay, this radiometer actually measures the radiation intensity from this hot surface in watt per meter square. So as you move forward, the radiation intensity increases. As you go away from the surface, the radiation intensity decreases. So basically, the radiation intensity varies as the square of the distance from the hot surface. So for example, I can place this at as close as possible for initial reading. So I can take this reading as a I1, and the distance from here I can take D1. So this one is I1. So if I move from this place to a distance D2, so I1 D1 square should be equal to I2 D2 square. Okay, this is basically the inverse square law of radiation. So as you move away, the radiation intensity decreases as the square of the distance. Okay, so this one is the bench is marked the scale in centimeter so that we can measure the distance from the hot surface. And on the other side, there's a gray surface. I can mount a black surface as well and a shiny surface as well on this unit. This is basically to study the surface texture. What is the effect of the surface color on the heat absorption of the material? So as you know that the black surfaces absorb greater amount of heat as compared to shiny or gray surfaces. So that's why we can perform another experiment on this equipment. So we are not doing that in our lab yet. That's not the part of the course. But right now I've mounted it at this location away from the heating element because I can assume that this gray surface is actually at the room temperature. So I can measure the room temperature using this gray surface. Right now I can see that on the panel I have connected the wire from the gray surface at the control panel. So you can say the temperature of the gray surface is 18.3. So that's, you can assume the room temperature. On the left of it, that's the temperature of black surface. Actually, that's the surface of that's the temperature of the heating surface, because the port T4 was not working. So I just replace it with the black surface in the T1 So T1 is the surface of hot temperature. The heating element surface, or the surface that is emitting radiations. So these two temperatures are required. The surface temperature, the heating surface temperature is 39.5, and the room temperature is 18.5. So the bottom there is a radiometer reading. There's a bit fluctuations. So these are the basic parts of the equipment. So you can see there. Okay, radiometer. In the first part, the objective is that the radiation intensity is proportional to the square of the distance, as I have discussed before. So what I have to do, I have to check whether the radiation intensity varies as the distance of square. So for that, I1 D1 square should be equal to I2 D2 square. So I would measure the radiation intensity at different distance. For example, I can point it at as close as possible. So this one, the radiometer reading would be I1 and the distance would be D1. So if I move away, so this is I2 and the distance is D2. I can measure at 5 centimeter 5 centimeter gaps. So for that, these all values must be match. So that's the basically the first experiment we can carry on this one. Okay, for the second experiment, what we have to do, we have the second objective is to show that the intensity of radiations varies as the fourth power of the surface temperature. This is the Stefan-Boltzmann law, as you can see here. So E is proportional to the surface temperature, the fourth power. Sigma is the Stefan-Boltzmann constant, and E is the emissivity. So I know the value of the E, the radiations emitted by the surface, and I know the value of sigma. I can measure the surface temperature Ts, and the T infinity, what I can calculate from here, the emissivity of the surface. So that's actually very small, so I will measure the value of 1 over E. That should be approximately the constant over the range of the temperature we will measure. So though there's a bit effect of temperature on it, but we can assume that in our reading that's approximately is a constant. So in that experiment, I'll have to basically measure the radiation intensity emitted by the surface. So for that, I'll place the radiometer as close as possible. So at this distance, I can measure the radiation intensity E, and using the formula, I can calculate the emissivity value, and reciprocating that, I'll get a constant that should be approximately constant. Moreover, I want to basically, there's a bit correction we use while using this radiometer, because the radiometer is measuring the infrared radiations emitting from the surface. So basically the environment contains the infrared radiations too. So for that we use basically use the value, the safety factor, the correction factor given by the manufacturer of 0.724. So whatever the value we get from the radiometer, we will multiply that by 0.724 to get the actual value. So this is about the experiment. Any question you can ask. And this is it. Moreover, there's another unit as well. Right here at the back, there's a light source. Okay, so we can perform the light experiment on this as well as compared to the infrared radiations. We have light intensity meter to measure the value of the intensity at different points on the surface. That's also possible. These are the capabilities of this apparatus. Hopefully you understand. Any question you can ask in class. Thank you.